Okay. Whoa, what? Yeah, yeah. Yeah, good luck maintaining anything with that. Yeah. Well, okay, I'm not sure what exactly this clip is supposed to do. Let's see. I think maybe I should just not worry about the clip too much. Oh. I have no idea how I was going to debug that. Okay. All right. So, what we have on the board is the essence of what we had last class when we were doing memorization. Remember that? Okay. So what I want to show you today is an alternate technique that is again about the same basic idea. The basic idea is, I'll remind you, we have a computation. The computation has several sub-problems, and what we would like to be able to do is when the sub-problems always produce the same answer, basically when they are functional, given an input, they're always going to produce the same output for that given input. We would like to remember that sub-problem's answer so that we can, what? Reuse it later. In particular, we are trading space for time, time for space, right? So we have that trade-off, and as I said at the end of last class, it's not always a given which way you want to take this trade-off, but typically for the kinds of applications most of you would write, most desktop applications, server applications, where space is more plentiful and it's not really that constrained, and time really could be an issue, you really want to do that trade-off, okay? So I showed you one technique, which is memoization, and the nice thing about memoization is it's basically like this black box technique, meaning I have an existing function, I slap memoize around it, boom, I get a memoized function, okay? I'm going to show you another technique this class, which is actually more common in traditional computer science presentations, and that is something called dynamic programming. The words don't at all mean what you think they mean. It actually, the word programming as they meant it doesn't mean programming as we mean it, so don't worry. It's just a term of art, okay? And it just happens to be called dynamic programming, and let me show you how dynamic programming works. So, the setup is going to look very similar, okay? We've got some memory, something that remembers in and out inputs versus outputs. We have some cache of previous things that we've seen. And the essence is still going to be, we're going to try to find an answer. If we find the answer, we're going to return the corresponding out value. If we don't find the answer, we're going to say, sorry, we're going to raise an error saying it's not there. Okay? So far, so good? Okay. So, let's start with something simple. Let's start with our Fibonacci example. So, okay. So if we find the answer, right, we're going to return the corresponding out. Otherwise, we raise an error. And the error is going to say something like, we should never have gotten here, right? This is the point of that error, is it should never be the case that we ask to look up a subproblem that, well, what did we do in the none case? I set this up and like I was hoping by now somebody would have raised their hand and said something, and nobody said anything. Yeah.
Where do you actually calculate that?
Yeah, where do we calculate? What happened last time? Is this the code we had last time? What was different about the code we had last time? There wasn't an error, right? Where was the error in the memoized version? Think hard, think hard. Talk to your neighbors. Remember where the error was in the memoized version. Okay, people remember where the error was? You don't have, I mean, obviously you're not going to remember the line number, right? Hello, 5, 4, 3, 2, 1, back. Okay. Where was the error? There was no error. Aha. Okay. So that is the major difference. There was no error. Now we're going to do a somewhat different thing where there is a possibility for an error. Okay. So what we're going to look it up, and basically we should only look up subproblems for which we already know the answer. That is the essence of the difference. Okay? I will put this difference in more abstract terms as we go along, but I want to start out very concretely. The essential difference between dynamic programming and memoization. In memoization, when we get to a subproblem for which we have not previously computed the answer, we go off and compute the answer and then, remember, use the C word. What was the C word? Cache. Loudly. Cache. Okay? We cache it. Here, we assume that we only ever look up subproblems for which we have already computed the answer. Okay? Assume we only look up such subproblems. So if we ever get back an answer that says none, that means we should not have looked up that subproblem. And that means there's an error in our lookup process. Okay? Okay, so let's have a little helper that tells us a set fib that given at a given location, the value of the Fibonacci is n, right? So all I need to do is I need to say memory is updated with link of mem of n comma v. Okay. Now, what would be a slightly more sophisticated version of this? Is that better? What would be a slightly more sophisticated version of set fib? Yeah.
You could have a block and return memory.
I could, but it's global. It's already available, so. Yeah.
The whole array thing you were doing.
We could use a different data structure than a list, absolutely. So, but that wouldn't be local here, right? I'd have to change other things as well. Yeah.
Maybe you could check if you already.
Yeah, you can check if it's already there. Exactly, right? I'm just naively adding it on. Okay, so we could check if it's already there. So there are two choices. We could arrange it so that we never put something in there that's not already there, or we could check that it's already there. Okay. So I'm gonna set it up in a way that won't matter, but you know, let's just keep that in mind. But I want to get to the essence of the idea, and to get the essence of the idea, is it okay to put it in more than once? Why is it okay to put it in more than once? Why is it okay to put it in more than once? Yeah.
It's a function, so it's going to be.
It's always going to produce the same output. So it is maybe going to slow down our lookup a little bit, especially since we're using lists and stuff, and we should be more sophisticated than that. But it's not going to change the outcome of the answer. Okay? We're still going to remember things, and the answer would not be different because we said put it in there multiple times. Okay, good. So now we need a way of setting up the table, right? So I need to know some sort of like maximum value that I'm going to look up, right? Because I can't set up an infinitely large table, right? I can't say, well, just set up the table for all time. So I need to say something about how many values I want in that table. So I'm going to set up to n, right? And basically what are we going to do? We're going to say for each value k in the range 0 to n. Now, slightly tricky thing. Range actually goes from 0 to n minus 1. So if we want it to go all the way to n, we have to get the range up to n plus 1 so that we get all the values from 0 to n. Okay? It's minor detail. Okay. So for each of those things, we're going to say set fib of k. Well, what's the value of the fib at k? What's the value of fib at k? Fib of k is what? Yeah, it's just fib of k minus 1 plus fib of k minus 2. Right? And we have fib already looking it up for us. So we can just look it up and we're done. Okay? Okay. Sorry. Okay? So, I can now set up fib of 10, say. Okay? Right? So what's setup fib going to do? It's going to go and populate memory with the first 10 or first 11 Fibonacci values. Okay? And then whenever we need to, we just look it up by calling fib of whatever. Okay? Good?
No.
No? Okay, talk to your neighbors and tell me whether this is okay or not. Go. I want an agreement. I want to know. If you say no, I want to know why. You can't just say no. The guys just like nod your head at me. Go.
And then you can set up like 0, 1. Set up this. So it goes fib of 0 minus 1. And that is nothing in that. Yeah. If you get
Okay, in 5, 4, 3, 2, 1, and we're back. Okay, how many of you think this is okay? Not okay? How many of you think this is basically okay? Okay. All right. Next question. Am I going to get an error when I hit return now? So, talk to your neighbors and tell me whether I'm going to get an error when I hit return now. Go. Talk to your neighbors. Go, go, go.
fib of minus 1. Fib minus 1 is fine. There's nothing in there. It's going to try to look it up, but memory is, I think, yeah, well, like the first one is done. It's fine. It's fine.
Okay. 5, 4, 3, 2, 1. We're back. How many of you think I am going to get an error now? Okay, that's pretty strong. What is the most important thing I need to fix here? Point to a place where I need to make a fix. Up, down, left, right. Around there? Up a little bit? Right there? One more line. I can't see any lines. There? Right there. That's the word from.
You moved it down again.
Okay. Up a bit. N, you want me to change the letter N? Would you prefer the letter P or what? Which letter would you prefer? Okay, where do you want me to make the change?
Right.
Right a little bit? Right?
Okay, that's good.
Right there? Right now I'm asking for the Fibonacci values of starting from 0, meaning that I'm going to ask for the fib of minus 0, minus 1, and 0, minus 2. Fib of minus 1 and minus 2. Really, I want to not be doing that, right? I want to be doing from 2 onwards, right? The iterative process starts at 2. Okay, so. Okay? Everyone okay now?
No.
Why not? Am I going to get an error when I hit enter?
Yes.
Why? Well, shall we try it out? We try it out? Yes? No?
Computer science is not experimental science.
Computer science is not an experimental science. Okay, we found the math geek in the class. All right, math department's over there somewhere. Hey, ready? Yes? No, you won't let me even hit enter? Well, screw you, I'm going to hit enter anyway. Okay, what's going to happen when I hit enter, mathematicians? Okay, did not have gotten here. Okay. And the trace is basically I called setup fib. I went there, and the first thing that I tried to do basically raised the error. Okay? Why did it raise the error? 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 New hands, new hands. Why did it raise the error? Why did it raise the error?
It's not defined on 0 and 1.
It's
Not fine at 0, no. Memory is empty also.
memory is empty. Okay, so basically the problem is we haven't actually set it up. So when we ask for fib, so when we go here and ask for the value of memory, it says there's nothing in there. Okay? So, how do we fix this? Talk to your neighbors and tell me how you want me to fix this.
You could also do it like
Oh, this is
the entire function is Fibonacci. So like this is not put it then before the 4 you have to put it
I was
How many? 5, 4, 3, 2, 1. We're back. How many ways can we fix this?
at least 2.
At least 2. Okay, anyone got more than 2? How many say 1? How many say 2? 0? Is there some other number? I'm not hearing very many votes here. Okay, let's try this again. How many ways can I fix it? 1 way. 2 ways. What are the rest of you voting? 3? 3 or more? 3. Okay, how many for 3? 4? 4? Okay. All right, I think I'm being trolled. I don't trust any of you anymore. Most of you anyway. Okay, give me one fix. One fix, yeah.
Between lines 19 and 20.
I love it. Between lines 19 and 20. Perfect. So I can do something between lines 19 and 20. That's one place I can do fixes. Okay, any other places I can do fixes? Yeah. Line 5. I can take a fix up there. Any other place I can do fixes? Yeah.
Line 6. Empty and then out.
Fine, line 6. Okay, good. Okay, any other places I can do fixes? Yeah.
Line 10.
Line 10. Oh, line 10. That's interesting. There was another hand back there. Yeah. Line 10. Yeah.
Between 7 and 8.
Between 7 and 8. Okay. Any others? Any others? Okay, I think at this point we've like asset stripped this program, right? We've like found every possible place we can. Okay, anyone in line 2 maybe? Any, change the date definition? No, okay, all right, nobody's that ambitious. Okay, so what could we do over here? Let's just make sure we all are on the same page. The problem here is we haven't actually given the base cases for the Fibonacci function, right? We haven't said what fib of 0 is, we haven't said what fib of 1 is. So the problem is manifesting itself as we don't know what needs to happen in the base case. And there's a few different places we could fix it. We could go in here and basically say what fib of 0, fib of 1 is. We could go in here and just initialize memory to have the right values. We could go in here and say if you're asking for the fib of 0 or the fib of 1, I can return that value, and then it sort of never enters into memory at all. I'm guessing that the line 6 people are basically taking lines 19 prime and 19 double prime and moving them up here. Is that what you're planning to do? Yep. And then what was the other suggestion? The more interesting case was line 10. What do you want to do on line 10? Do you both want to do the same thing? Have you talked to each other? Okay, talk to each other for a moment. While they're talking, the rest of you can also talk. What do you want to do on line 10?
blow things up and let's do a you guys how much time a linear lookup takes?
Okay, 5, 4, 3, 2, 1. We're back. Do you have an agreement? Okay, what would you like to do on line 10?
Ask for n equals 0 and n equals 1.
So, okay, so in line 10, we will change that raise to basically do an ask and then do, that's sort of like doing it at between 7 and 8, right?
Yeah.
It's roughly like doing it between 7 and 8, but you don't do it unnecessarily. You don't ask the question unless you need to. Okay, so here are our candidates, okay? So we have the choice of doing it on line 5, line 6, which is basically set the initial values over here. Line, line between 7 and 8, right? Basically putting in some ask over there. Line 10, line between 19 and 20. Did I cover all of those? Okay, we're going to vote. Talk to your neighbors and tell me which of these you're going to vote for. I think I'm going to allow multiple voting. Yeah, I'll allow you to vote. I'll let you vote for more than one, but if I find like all of you are being a little fuzzy about it, I'll force you to pick one. Go.
Definitely want to do because like when you call setup, call setup and then set.
You look up anyway. You have to go and do and it will be at the very end.
Okay, so let's ignore the fact.
This is our data structure. It's much more efficient and so much easier. It is, but it's a lot more efficient if you are checking your constant words.
Five, 4, 3, 2, 1, and we're back. Okay, how many vote for line 5? Wait, you can't wait for other people to vote and then start voting. You got to make up your mind. Line 5. Line 6. Line 7, 8. Line 10. Line 19, 20. Oh, okay, all right. Okay, we have a clear winner. Anyone want to vote against these? Anyone want to vote against 5? Just for hum vote. Vote against 5? Ooh, 6, 7, 8, 10, 19, 20. Aha, that was the better vote to take. Why are you all so judgmental about the other things? Yeah.
So it seems like, okay, so for 5 and 6, you're unnecessarily making memory Fibonacci dependent.
Aha!
For
Aha! So with 5 and 6, we're building a dependency of Fibonacci into this memory data structure, okay?
For 7 through 8, for 2 reasons. One, if you do it in 7, 8, or even 10, you're not really changing much from last class. So it's the same exact idea of memorization.
Okay.
But the bigger issue is...
well, it's not the same exact idea, right? We're not memoizing. We're only doing it in the base cases. We're not, in the other cases, we're still going to be doing a lookup.
That's true.
Yeah.
Okay, bigger issue is that right now, as it is, that Fibonacci, that fib function has actually 0 dependence on fib, and we'd like to keep it that way.
So it's just a lookup function. It's sort of fib independent, right? Yeah. Okay.
That covers 7 through 8 and 10.
Yeah, and then there's nothing left.
Yeah.
Okay, so in some sense the logic of fib has all been moved. So the advantage to putting it between 19 and 20, the entire logic of Fibonacci is now self-contained in 1920, right? It's no longer elsewhere. Like everything else is now essentially completely generic, right, for a one-argument function, and it doesn't depend on anything else. There's actually a subtler thing about doing it on line 10. I really like the line 10 suggestion. Because here's what's going to happen in line 10. We could put in an ask statement. We can ask, are you n is 0, return 1, n is 1, return 1. But then we're stuck with an otherwise. And we still have to do something in that otherwise, right? And in some sense, all we've done is remove the hack one level down, right? We've just patched one level and we still have to deal with the otherwise in that case. And in the otherwise case, we really want to say the same thing. Raise should not have gotten here because we don't want to put more logic in there, right? It's the base cases where there's no sub-calculations. There's nothing gained necessarily by remembering them. But in every other case, the whole point is we want to avoid recomputation. So we're anyway going to have a raise should not have gotten here DP failure in the otherwise of the ask on line 10. So why not just leave it at the top level and move all the logic elsewhere? Okay? So my own preference would be for this, for basically the reasons that you articulated. So okay. Quick test to make sure you understand. Talk to your neighbor and tell me what I'm going to write over here. Now, go. I want everyone to be able to call out the code to me. Go.
You need a block.
Okay, everyone know the code? Read out the code to me. Go. Go, go, go. Read. Yell it out, everyone. I want to hear everyone. That wasn't very good. Okay. Okay, yeah. Okay. Okay. Set up fib of 10. And now, if I look at memory, right? And so if I say a fib of 10, I get the answer that I expect, okay? What happens if I now say set up fib of 100? Would that still work?
Yep.
That work? What is memory going to look like? So memory is going to have all of those values, right? But then over here we're going to have some repetition, right? Because we still have that old value. So now I can say fib of 100. So now we know, I mean, it's already done calculating, right? Now we're back in math land, right? We have a giant table and we're just looking up a giant table, right? And so this is unsurprisingly going to take constant time because the value is already there, okay? Good? And let's just do some familiar values just to make sure that that looks about right, and 55, 34, etc. Okay? Very useful for one purpose, by the way. I know of only one use of the Fibonacci. Miles to kilometers. Right? Because the limit of the Fibonacci sequence is phi, 1.61. Miles to kilometers, 1.609. So when you go, like when you drive into, Ontario, for example, you see like a 90 kilometers speed limit there. 90 is 89, 89 is 55, so you know it's 55 miles an hour. So very useful for that purpose. I don't know of any other use for this silly thing. Okay, so, so here's what we've done, okay? We have managed to, I like this idea that we have this very generic code over here. All of this is kind of fib independent. But, it's actually not as independent as you think because, yes, this mechanism is all generic, but this mechanism here is where the essence of the fib is. And this is actually a rewrite of the fib function, right? We had to rewrite. In fact, there is a way we could have gotten this wrong. I mean, we actually saw one way we did get this wrong, right? We forgot to initialize. But there's actually another way we could have gotten this wrong. Tell me what I could do to get this wrong. I can add 1, 2, 3, 4, 5, 7, 8, 9 letters and get it wrong.
Raise parentheses.
Raise, yeah, I could always add a raise. There's something subtle here that you haven't quite noticed. Something very subtle here inside the function setup fib. Look carefully at setup fib. There's something subtle and you may not have realized that it's even subtle. I mean, this is totally going to be like, oh, come on, when I tell you, but it's a true thing. Anything at all? Anything at all? Yeah.
Is it that it's dependent on the last two, or it's like other sequences might not be?
No, no. So this is not a statement about what Fibonacci is. Well, it's a fib-related thing, but it's really about the way I've structured the code. There's something about this code that makes it work that if I made small changes to the code would not make it work. Would make it not work. Yeah.
Even right now, if you call like setup fib of 1, you'll get like 2 things in memory.
Yeah, that's fine. That's okay. I'm only interested in cases. The only reason I'm doing this is because I have sub computations, right? So yeah, yeah.
If you did k minus 2, then k minus 1, then it would break.
K minus 2.
Just kidding. I lied.
Yeah,
I was thinking.
that
I
was my first
I was thinking the other way
thought,
around. I was
but
thinking for memoization. Never
No,
mind.
no, you're onto something. What order does range produce values in? What if I reverse the list? What if range happened to produce things in the reverse order? Would this work? Right?
No,
Yeah.
it's stopped.
Yeah, it's stupid. Okay. Right. So there was actually a very implicit dependence in this setup line over here that we arranged it. Now listen carefully because this is critical. We arranged it so that all the sub-problems will have been computed before we try to compute the super problem. All the sub-problems had to be computed before we tried to compute the super problem, right? So we had to make sure that these are independent of each other, so these could be in any order. But then it was really critical that we went from 2 to n plus 1 and not from n plus 1 to 2. Compare this to the memoization case. What order did things happen in the memoization case? When I asked to memoize, yeah, what order? Top to bottom. So what was the first thing that got called? Like if I do a straight Fibonacci of 10. Fib 10. What was the first thing that got called from there? Fib 9. But Fib 8 happened before this Fib 8 happened, remember? Remember, like the tree, right? Fib 9, this Fib 9 happened. This Fib 9 called Fib 8 before this Fib 8 happened. And Fib 8 called Fib 7. And Fib 7 called Fib 6. Remember that? So we actually started with big problems and went to small problems. Here, if we try to do exactly the same thing, go from big problems to small problems, we end up with errors. We actually have to go from small problems to big problems. Let me tell you something a little subtler. I actually did something. Now, this is a critical thing because you will not see this in your later computer science education when you do dynamic programming. Okay? I was able to generate an error. Why? Why was I able to generate an error? What enabled me to detect and generate an error? What enabled me to detect and generate an error? There's a one-word answer. Yell it out. Well, raise is the thing that raise did not detect the error. Raise is the thing that printed an error.
Empty.
What's the thing that enabled me to detect and generate an error? Yell it out. Option. Option. I did not make this. I used the fact that I had an option to look it up and actually report an error if it wasn't there. When you traditionally do this using an array, what you will typically find in your textbooks is you'll have an array, and the array will be of the same type as the value that you're trying to eventually compute. So if I'm trying to compute numbers, you'll have an array of numbers. Here's the two problems with that. There's always an array index available, unlike the list where I had to look it up and it may not be there. In the array, there's always there. If I say ask for array of 8, something's there. And if I store a number in there, I'm going to get something that's indistinguishable from a true answer. Right? So if I set this up just wrong, I won't get an error. I will just get wrong answers. And when you do dynamic programming later on, starting next semester, and you'll do dynamic programming in several of your future courses, just keep this in mind. If you can, set it up as an option so that you'll know if you accidentally stomped on a value that's not yet available. You need a way of detecting whether the value is available or not. Okay? If you don't, make sure you have another implementation, maybe like the simple recursive implementation, maybe with memoization, maybe even without memoization. With memoization is obviously good because it'll run a lot faster, so that you make sure you got the answer right, because otherwise you'll just get some mysterious number and it may or may not be the right one. Okay? Keep this in mind. I know you'll probably forget it, but just remember this, because this is an error that people do make when they use dynamic programming. Okay? So the critical thing here is we were dependent on this giving us the right order, and that's the only reason it worked. Okay? And all of this works. So what I want to do, before I do another example, I want us to talk a little bit about the difference between dynamic programming and memoization. So there's a lot of confusion in computer science textbooks. These are actually two very different techniques, but oftentimes people will use the same term for both. And traditional algorithms books will actually give you the dynamic programming solution and won't even show you the memoized version. Like, they don't even tell you that's a thing. I guess people are afraid of recursion or something like that. So you're more mature than that, so it's not a problem. The critical difference between dynamic programming and memoization. Memoization is a top-down solution. You start with the biggest problem, you compute its subproblems, and you go all the way down. Every time you compute an answer, you remember that answer. If you ever need that subproblem again, the answer is sitting around and you look up the answer rather than computing it. Okay? Dynamic programming is a bottom-up solution. You start with the subest problems and then work your way up towards super problems till you get to the super problem that you actually cared about. Okay? So you have to arrange your computation so that you have all the subproblems computed before you compute the super problem, and it becomes your responsibility to make sure you arrange things in just the right way. Right? Because if you don't arrange it properly, you could ask for the wrong answer, and if you set up with the wrong data structures, you'll even get an answer even though it may be the wrong one. Okay? Does that make sense? So dynamic programming is bottom up and memoization is top down. Another way we can look at this is simply look at there's what the trace looks like. Remember, we had this nice tree, and we had this tree, and then once we memoized it, it became a DAG, and it became kind of a skewed tree, right? This thing is completely flat. All the subproblem structure has been lost because we're linearly walking this data structure and setting up all of the pieces. So this resembles the structure of the data structure in which you're storing things, not the structure of the computation you were trying to achieve. Okay? Like, basically we took this sideways thing and kind of tilted it this way because we have a linear data structure instead. And next class we'll see a case where we have a two-dimensional data structure, and so you kind of have to do a sort of pattern of sort of rolling out to make sure you have the right subproblem solved. We'll see that next class. Okay? Another way to think about it is, you've all seen now breadth first and depth first things, right? Breadth first traversals, depth first traversals. So if you think of the space of problems, dynamic programming is breadth first. It solves all of the subproblems before it tries to solve the super problem. So it explores subproblems, then the super problems, then the super problems, then the super problems. Memoization is depth first. It solves the first subproblem, which solves the first subproblem, which solves the first subproblem. When it finishes, then it starts to solve the second and third subproblems and gets to reuse all of the previous solutions. You should ask yourself a question. So now I have given you a name for top-down depth first. That's called memoization. I've given you a name for bottom-up breadth first. That's called dynamic programming. What is the name for top-down breadth first or bottom-up depth first? What would such a thing look like? Think about it for a moment. Talk to your neighbors. What would a bottom-up depth first or top-down breadth first look like?
I think it's kind of like you could try to do top down. That's like oh yeah. Maybe a little bit
So, depth first, memoization, breadth first, dynamic programming. If we try to go from the top down, but try to do things by breadth, we'd never solve any subproblems till we got to the bottom. So we would never get to reuse any previous solutions. So it would be completely meaningless to try to do that. You would get no reuse at all, and the whole point is we want to avoid recomputation, but you'd never finish any computations to avoid recomputing it. The same way, if you start from the bottom and went all the way to the top anywhere, well, you'd never finish any computations to be able to reuse the subproblems either. So it has exactly the same problem in dual. And that's why we don't have a name in computer science for the technique of breadth first top down or depth first bottom up, because neither one gives you any benefit, because you never get to finish any sub-computations to reuse for doing super computations, or you never solve any sub-computations to use for doing super computations over here, right? So there's no name for those techniques, and for a good reason. They don't make any sense. You'd be very stupid to implement such a thing. Yes?
Doesn't bottom-up depth first have the additional risk of just never finding your super?
Yeah. So there's a lot more other issues as well, like how do you know where to terminate, etc. Okay? So that there are lots of good reasons why those things don't exist. Okay? Now, yes?
What is it about dynamic programming that is preferred over memoization in most textbooks?
Well, historically, people have been afraid of recursion. There's a long, complicated story for why, but they're just afraid of recursion. And so it's like recursion is evil and you've got to root recursion out. So we will rewrite the program into a non-recursive version so that we don't have to use a recursive version. That's basically the short version of it. Okay? So in the book, I actually discuss this trade-off quite a bit more because there's a few more things going on, just to give you a sort of fuller account, right? So we've got top-down, bottom-up, depth first versus breadth first. Dynamic programming really can't be a purely black box. So it is the case that certainly some of this code can be pretty generic, but this, we have to rewrite Fibonacci. We can't just use the existing Fibonacci code and slap something around it. We have to rewrite it in a way that respects the ordering of the subproblems to superproblems, right? And that is potentially a rewrite you have to do. So you cannot make it a purely black box procedure. There's more interesting things. So with memoization, every call that is made had to be made. It had no choice, right? We only store the things, like we only make calls that we need to make in the process of computing the solution. In dynamic programming, you can't be sure. It may be that because you're doing this breadth first thing, right? It may be that when you get up here and this was the problem you actually wanted a solution to, you only needed this subset of solutions. You didn't need this other subset, but too late because you're working bottom up. Okay? On the flip side, with dynamic programming, so this is one advantage dynamic programming has, you can shrink the memory use. Because you know as you're working bottom up, you don't need some previous solutions. The classic example is actually Fibonacci. you can shrink that entire array into two variables, just the two previous values. You don't actually need all of the previous values. Catalan, you do need all of the previous values. With Fibonacci, you don't need all of the previous values. You only need the two previous values, and you can keep accumulating. So you can save space. It's hard to save that space in this version. So if you know you need only one particular super problem and you don't need multiple of them, you can throw out some of the unnecessary ones. But that requires, again, somebody to have the insight to say, you know, I never touched all of these previous values after a particular point. Okay? You can't do that trade-off over here. Flip side is, you can never accidentally use an uninitialized answer. That's not even a concept, right? Because in that none clause, we went off and computed it. In the dynamic programming case, that is a possibility. When you see dynamic programming later in your algorithms textbooks, look at whether they talk about that or not. Many of them don't, right? But implicitly, there needs to be a guard making sure that that value is actually in place before you use it, right? On the other hand, you pay a price for that. In memoization, you have to check whether the answer is there or not, because if it's not, you have to go and compute it. If you are careful in the way you arrange your dynamic programming, you never need to even ask for that question because you were careful to guarantee that the subproblems were all computed. So every one of these things is a trade-off. Like they really are duals of each other. Everything has a strength in one place and it turns into a weakness in the other place. It's exactly like duals between the two. Okay? So this is a trade-off that's not very well explained in later courses and in computer science texts. So I feel like I want to spend a little time helping you understand this. Supposing you have a problem where the space really matters and you're able to like throw away a bunch of space and reuse memory, that suggests you should use dynamic programming. What use is a memoization solution then? Is there any use at all?
The separation of concerns.
Well, yeah, but you don't want to use it. Like you want that space. You can't afford to use that space, or you really don't want to use that space. Yeah.
You can use it to check.
Testing. Testing. You're more often than not, you're going to use these on things that are mathematical formulas. Okay? They will almost certainly be naturally recursive. The memoized solution will give you the natural recursion. You just write the reference implementation, you slap a memoize around it, boom. You have an efficient testing oracle. Right? So even if what you really need is a dynamic programming solution, always think about writing the memoized version at least as a testing oracle so that as you improve that, because you'll come up with clever ideas, right? Well, can I throw away the space? Can I use this other data structure? Maybe I found some clever like hash table thing. Maybe I found like a clever probabilistic data structure to use. These are all perfectly legitimate things to do. But as every step goes on, you're getting further and further away from the essence of the solution and getting more and more into implementation ideas. It's even more critical. Or you might say, you know what? I think I got the order of computation just right. I can throw away the sort of the option type and I can live dangerously. Right? Great. All the more reason you need something you can test against. So it's always useful to start by writing this. Here's the other thing. Most of the time you start by writing this, you'll find it's fast enough and space efficient enough and you're done. And you can move on to something else. There's always like 100 other things to do when building a system. This is now a solved problem. You can leave this solution intact till you discover this is where your bottleneck is. When you do, move this into your testing harness, do the transformation. Make sense? In the book, I show you how to do an array version of Catalan. So just so if you want it for contrast, I do have up here a up here I have an array version of Catalan, and the next class we'll get to a more interesting example that's two-dimensional and has some other applications as well.